All right, here's your second lesson of the week on probability. So we're going to look at a lot of the same stuff, but looking at it in different ways. First one's going to be a little bit different. We're going to look at the probability of multiple events. So what if more than one thing happens? In general, there's two situations where this can occur. Number one, the two multiple events might not affect each other at all. So if they don't affect each other, then you simply do the probability of one event times the probability of another event. So this would be like the probability of on this die rolling a 2 and the probability on this die rolling an 8. Okay, well, the probability of rolling a 2 on this die is 1 out of 6 because there's 1, 2 out of 6 sides. And then the probability of rolling this die is 1 out of 8 because there's 8 sides and I want to roll an 8. But rolling this dice is not going to affect rolling this dice. There's no magical connection to them that if I roll a 2, then a certain number on this one has to roll. So those we would say that those are mutually exclusive events. So those are pretty simple. We just multiply the probability of this one rolling a 2 times the probability of that one rolling an 8 or a 2 or a 1 or something else. Okay, so it's just multiplying the two events when there's two or multiple events occurring. You just multiply their probability together. So that's if you want to know the probability of two things happening at the same time. Okay, but what the more important one is dependent events, the ones that do affect each other. I really wrote this badly. But this is the probability of A times the probability of B given that A has already occurred. So when does this happen? Okay, let's say that we've got a cooler, and in that cooler, there's 10 Dr. Peppers, and there's 6 Mountain Dews, and we're going to pull some drinks out of that cooler, and we win either way because Dr. Peppers and Mountain Dews are delicious. Okay, so we're going to win no matter what, but we want to know what's the probability of pulling out 2 Mountain Dews. Well, since I'm pulling out 2 Mountain Dews, my first pull is going to affect my second one, because in my first pull, I'm going to pull out a Mountain Dew, and I'd be happy 6 times out of a total of 16. There's 16 drinks, and on my first pull, I have 6 chances to pull out a Mountain Dew, and we're just assuming that we're pulling them out here randomly without looking. So for Mountain Dews, I've got 6 favorable outcomes, and there's 16 different cans of soda in there. So 6 out of 16 times, I'm going to pull out a Mountain Dew on the first pull. So if I reduce that, that reduces to 3 out of 8. All right, that's my first. Now the second time I pull out a drink, I've already pulled out 1 Mountain Dew. So I don't have 6 Mountain Dews left. I've only got 5, which also means that I only have 15 drinks left because I've already pulled out 1 Mountain Dew. So on the second pull, if I want to pull out a Mountain Dew again, I don't have 6 of them anymore because these are dependent events. Since I've already pulled out 1, I've got 1 less Mountain Dew to pull out. So, Mountain Dew. So I've got 5 Mountain Dews, and this time there's only 15 cans of soda to pick from. So it'd be 5 out of 15, which is 1 out of 3. So pulling a Mountain Dew the first time has changed my chances of pulling out a Mountain Dew the second time because they're dependent. So this is what we're talking about, the probability of B given that A's already occurred. I've already pulled out a Mountain Dew, so that has changed the chances of pulling a Mountain Dew the second time. And so if we wanted the probability of 2 Mountain Dews, we would have to multiply these 2 events with each other. So we'd have to do 3 over 8 multiplied by 1 over 3. So if we multiply that, we multiply going across, we get 3 over 24, which reduces to 1 over 8. Or that would be point, what is that, 0.125? I don't know. Wrote it down somewhere. Yeah, that's 0.125. 0.125. Now sometimes they ask you to write this as a percentage. As a percentage, you just move this over 2 spaces and you'd say, or this is 12.5% of the time. So you just move that decimal over 2 places and that gives you the percentage of it. Okay, so you just multiply the first probability times the second probability. All right, tables and Venn diagrams. So you've already kind of done tables, but we're going to see how they can be written as Venn diagrams as well. So here I've got a class of 28 students. 10 of them have a brother, 9 have a sister, and 4 have both a brother and a sister. You might be looking at this and going, wait a second, how's this all going to add up? Well, the first thing we have to do is do the both section. So I know that I've got 4 that have both. So in a Venn diagram, this section would be the brothers and the sisters together. So 4 of them have brothers and sisters. So this circle represents brothers. Now I said that there were 10 brothers. I don't put 10 here because I'm already counting 4 of them. So this means that there are 6 that only have a brother, and then there's 4 that have a brother and a sister. So that's your total of 10 having a brother and a sister. Then over here, have a sister. I've got 9, but I've already counted 4 of them here. So, oh, that was supposed to be 19. Let's change that. 19. All right, so yeah, they definitely don't add up right now. Right now I've got 33 students, but I said there's 28. So now we're figuring out why that doesn't work. I knew I wrote something down wrong. All right, so now that means that 15 only have a sister and 4 of them have a brother and a sister. So I still have in my sister circle, I have a total of 19. So 4 is the and, so this is brother and sister. So when I say that I have 10 with a brother, that means I'm counting 6 of them that have only a brother and 4 of them that have a brother and a sister. Over here, when I say I have 19 that have a sister, that's 15 that only have a sister, but 4 that have a brother and a sister. So that's how the and works in that. Okay, so let's add it up. I've got 6 plus 4 is 10, plus 15 more, that's 25. But wait, I had 28 students. Where's the other 3? The other 3 are students that don't have a brother and they don't have a sister. They would be out here. So that would be the students without a brother or a sister. All right, we can take this same information and we can put it into a table. So let's say that we wanted a total of 10 who have a brother. So have a brother would be 10 right here. That's total. And then if we wanted to do it on this one, say 19 have a sister. So sister would be 19. And then it says there's 28 students. So we put 28 over here. And then we want 4 who have both. So brother and sister. Here's the and where they intersect. That's 4. And so brother, no sister, they have to add up. That would be 6. So that's this number right here. Brother, but no sister. Over here, sister, but no brother would have to be 15 because 4 plus 15 is 19. Okay, how many don't have a sister? Well, we've got 19. Sorry. We've got 19 that have a sister, and there's a total of 28, so that means 9 of them don't have a sister. Which means over here, we've got 3 with no brother, no sister, which is over here. I said there were going to be 3 with no brother, no sister. That means we have 18 with no brother at all. All right, so let's look at our probabilities. Probabilities of having a brother. So total brothers is 10, and we can see here there's 10 that have a brother. So that's 10 out of a possible of 28. So having a brother, there's 10 out of 28. We can reduce that to 5 over 14. So we can leave it like that, or if they ask you to round it to nearest thousands, you just plug it into your calculator. Let's see that we want to find the probability given that we already know they have a sister. So if we're looking at the probability of a brother given that they're having a sister, so we're going to look at just the people who have a sister. There's 19 of them. So that's going to be our denominator. We're looking just for the ones who have a sister, and we want to know of those 19, how many had a brother? Well, there's 4 of them. And we can see the same thing up here. If we're looking at just the sisters, there's a total of 19 here. And of those, how many have a brother? 4 of them did. So it's 4 out of 19. So that doesn't reduce. It'd be 4 out of 19, or you'd plug it into your calculator. Okay, what's the probability of finding somebody who has a sister given that they don't have a brother? So we're only looking at the ones who don't have a brother. So over here, if I'm looking at this one, the ones that don't have a brother are this 15 and this 3. So there's 18 that don't have a brother. On the two-way table, we can see that same number here, no brother, 18. And we want to know of those 18, how many have a sister? Well, over here, of these 18, how many have a sister? These 15 do. We see that same number over here. Of these that have no brother, how many have a sister? 15. This can reduce. 3 goes into both of these, so this is 5 out of 6. All right, what's the probability of having no brother or no sister? All right, so on the Venn diagram, we want to find all the ones that have no brother or they don't have a sister. All right, so over here, how many of them do not have, of these people, how many do not have a brother? Well, there's 6 that don't have a brother, and there's 3 that don't have a brother or a sister. Okay, it's a little bit harder to see it on the Venn diagram, but if we go over here, let's go look for all the ones that have no brothers or no sisters. Let's start with no brothers. Okay, so no brothers would be a total of 18. That total is these 2 numbers. So no brothers, there's 18 of them. Now let's count all the ones who have no sisters. No sisters would be this one and this one. Okay, I can't just add up 9 and 18 because I would double count these 3 people. So I'm just going to add up the numbers of 15, 3, and 6. Those would be all of them that have no brother or no sister. So these 6 people have a brother but no sister. These 15 people have no brother but they have a sister. And these 3 have no brothers and no sisters. So the or means I can do any of these. I'd be okay with any of these 3 sets of people. So I've got a total of 6 plus 3 is 9, plus 15 is 24. So there are 24 out of a total of 28. And we can reduce that. It looks like 4 goes into there, 6 and 7. So 6/7 have no brother or no sister. Okay, let's find the ones who have no brother and no sister. So it means that they both have to have no brother and no sister. Over here, it's easy to see there's only 3 of them. And over here, we can see this is no brother, no sister. They both have to occur. So it's just those 3 out of a total of 28. And that reduces to nothing. No. Yeah, that doesn't reduce. Correct. So just 3 out of 20. So there you go. Last part. Probabilities given, they're giving you probabilities already. This can be a little bit confusing, but we have to remember that all of our probabilities are going to add up to 1. Because that means 100%. So let's say that we are looking at the New York Yankees. It says they win 0.56 games, which means 56% of the time they win. So over here I'm going to write 0.56. That's how often they win. So that means they're going to have a total of 1.00 games because that's 100%. So if they're winning 56% of the time, that means they're losing 44% of the time, because it has to add up to 100%. So they're going to win 56% of their games. That means they're going to lose 44% of their games. Okay, the next thing it says is they score 5 or more runs 61% of the time, 0.61. Okay, so 5 or more, so greater than or equal to 5, that is 0.61. Which means if 61% of the time they're doing 5 or more runs, that means 0.39, 39% of the time, they're not doing 5 or more runs. That's less than 5 runs. And these two have to add up to 100%. Now here it also says that the probability that they lose and score less than 5 runs, so lose and less than 5 runs right here is 0.32. Okay, that means we can fill out the rest of it. So if 0.32 of the time they are losing with less than 5 runs, that means that 0.07% of the time, or 7%, 0.07, they've got to win with less than 5 runs. Going this direction, we can see that this number should be 0.49. So this means that 49% of the time, when they make more than 5 runs, they're going to win that game. Okay, then over here, we can either add going here or going the other way. By the way we do it, this number here is going to be, what's that, 0.1 something. I can't think of numbers right now. I'm just going to write it down. It should be 0.12. Yeah, that adds up going that way. All right, so I filled out everything that I've got. I started with just this number and this number and this number, and then knowing that everything adds up to 100%, I can fill out the rest of those numbers. Remember, side to side they have to add up and down they have to add up. Okay, so I want to find the probability that they lose when they score less than 5 runs. What's this saying? It's saying that we want the probability of a loss, or a lose, given that they have less than 5 runs. So I'm only looking at the times when they have less than 5 runs. 0.39% of the time, or 39% of the time, they have less than 5 runs. So I want to know when they get less than 5 runs, what's the chances of them losing? And it says here that is 0.32. So I want to know what's the chances of them losing if they score less than 5 runs. And 0.32 divided by 0.39 gives us 0.8205, so 0.821. So what does this mean? It means when they score less than 5 runs, 82% of the time they're going to lose that game. So if you're a New York Yankees fan, you want them scoring more than 5 runs, because when they score less than 5 runs, there's a good chance they're losing that game, 82% of the time. All right, and that's all I have for this week. Have fun. Bye-bye.